Okay, so let's look at another problem. Same reaction, propane combustion reaction forms water and carbon dioxide. But how much oxygen do you need? Again, we'll be burning 200 grams of propane. Let's go through it again because it's almost the same question as before. Let's just lay out the steps in a little bit more detail. So, first step, find the molar ratios from a balanced equation. We've done that. Ratio of propane to oxygen is 1 to 5. So for every mole of propane that you have as a reagent, you will need 5 moles of oxygen. Determine the molar masses. Okay, also ratio of propane to oxygen. Determine the molar masses. Well, the molar mass of C3H8 is 44.097. We had looked at that before. And oxygen is 2 O's, so it's 29.998. Okay, so that's the number of grams for every mole that we have. But we know that we have 200 grams of propane, so how many moles is that? Well, we worked that out before. We have 4.535 moles. Multiply that by 5, and it will give us 22.675 moles of oxygen. So if for every 1 mole of propane, we need 5 moles of oxygen, we know we have 4.5 moles of propane, so we will need just over 22.5 moles of oxygen. 22.5 moles of oxygen, 22.675 moles of oxygen to be precise. Each has a mass per mole of 29.998 grams. So we're going to make 680 grams of oxygen. No, we're not going to need 680 grams of oxygen. 200 grams of propane will combust with 680 grams of oxygen to make the products. Just to review, 200 grams of propane plus 680 grams of oxygen. So we've said the 200, that's set. Now we're finding out how much oxygen we need, 680. We know we're going to make 327 grams of water. We worked that out earlier. So how much carbon dioxide are we going to make? Well, remember the law of the conservation of mass. When it comes to chemistry experiments, no mass goes missing. We had 880 grams, 200 plus 680. So knowing that we have 880 grams, we then take away the amount we're making of water, 327, and 880 grams minus 327 gives us a total of 553 grams. So 200 grams of propane, which we've decided, that's the number we were given, needs 680 grams of oxygen, and will make 327 grams of water and 553 grams of carbon dioxide. Again, this is really important stuff in industry. Or if you're looking at biological processes, okay, biochemistry, no matter what branch of chemistry you're doing, no matter what chemical reactions you're doing, it's vitally important to know how much you need and how much you're going to make. Speaking of which, what happens if we don't have what we need? Well, it's quite simple. If we don't have enough oxygen, if we have too much oxygen, that's called a limiting reagent. Now, for an example, suppose we're trying to send invitations to a party. We have 12 party invitations to send, but we have 20 stamps, yet each invitation needs 2 stamps. We want to send 12 party invitations, but we can't, because 12 party invitations would need 24 stamps, and we only have 20 stamps. We can only send 10 invitations. We're limited by the number of stamps. And it's the same situation for our oxygen. If we have 200 grams of propane, but we do not have enough oxygen, then not all of those propane atoms, the atoms in the propane, are going to be able to match up with the oxygen in order to react. Okay? So we're going to have all of the oxygen that we do have will be used up, but we'll have propane left over at the end. Similarly, if we have too much oxygen, that's the better situation, so to speak. The 200 grams of propane will be completely combusted, but we will have oxygen left over. Okay? And that can be a problem in an industrial process, because if you're supplying the reagents, you might be spending money on supplying stuff that just isn't being used. It's important to know what you need as well as what you get. And I think that's the big takeaway from this particular process. Thank you very much.